Hello everyone. Today our problem is a bit unique. No, this is not jalebi, though it looks like that. Okay, so this is a plane spiral. And the plane spiral has many turns. It has got capital N number of turns, suppose. And we don't know what is the value of capital N. Suppose it is a very large number. And the outer radius of this spiral is small a. Suppose you have a crossed magnetic field here in this region, and this magnetic field varies with respect to time, which is b0 sine omega t, and directed perpendicular to the plane of the paper inward. Okay, so b0 sine omega t minus k cap, which is b vector. So we have this plane spiral whose outer radius is small a, placed within this time varying magnetic field. So the obvious impact is that there will be some EMF which is induced. Why? Because with the changing magnetic field, the magnetic flux linked with this spiral is also changing. Our goal of this problem is to find out the value of induced EMF, or we should rather boil it down to this particular question, that we have to find the amplitude of induced EMF across the two ends of this spiral. Okay, so without any further ado, let's get started. Our first thing is that approach will be that let us consider a small part of the spiral of thickness dr at a distance smaller from the center. Okay, so that is our first thing that we need to consider. So that's what. So we have considered a small element of the spiral, say at a distance smaller from the center. If I consider a small part of thickness dr, and that dr length of the radial distance basically encompasses or covers dn number of turns. So magnetic flux which is linked with these dn number of turns, we can write it like this, that d phi equals to dn multiplied by b. What is b? b0 sine omega t into area. Area is pi r square. Okay, so magnetic flux linked or associated with these dn number of turns is dn into b into a. dn is the number of turns enclosed in this infinitesimal thickness dr along the radius. B is the magnetic field, time varying magnetic field, which has been externally applied, and pi r square is the area of this loop of thickness dr, which is primarily small r. Okay, so that is the area. So we can find out the amplitude or magnitude. We can find out the magnitude of induced EMF will be d phi dt. Okay, so you may neglect that negative sign which Mr. Lenz brought in. So if you do dn d phi dt, so dn is some constant at least with respect to time, then you will get pi r square b0, and if you differentiate sine omega t, you will get cos omega t, and there will be omega. Now what is this dn? How can we find out dn? So now you see dn, if I say the total number of turns, how many total number of turns are there? N, capital N. So that capital N number of turns is distributed in this radial distance a. So in the radial distance a, capital N number of turns are there. So in the thickness dr, how many turns are present? So what we can say, it is N divided by r divided by a, multiplied by dr. So capital N number of turns are distributed in the radial length a. So in the radial distance dr, how many turns are encompassed or enclosed is n by a into dr. Now you put this value. So therefore what do we get? So what we can write? We can write n by a. See, let's take the constants. Pi b0 omega, we have r square, right? So pi b0 omega cos omega t is also there, and then what else we can bring? Say some r square is there, pi b0 omega cos omega t r square, then dn is n by a multiplied by dr. Okay, now E is d phi dt. Now this is basically, I should write it as dE, or I should write it as delta E. I could have written as dE, I should have written. Why? Because this is the EMF induced corresponding to these dn number of turns. But if we want to find out the total EMF induced for all the n number of turns, then we must integrate it from 0 to a. Alright, so you please see this very carefully. This EMF which is induced is corresponding to these dn number of turns enclosed in the radial, infinitesimal radial length of dr. But what is the total EMF induced? We must integrate this radial distance dr from 0 to a. Okay, so we should write it dE here. If I write dE here, I will write it E here, and I can integrate it from r equals to 0 to r equals to a. So if I integrate this, what will I get? So from here, what will I get? I will get E equals to pi b0 omega capital N cos omega t divided by a r squared dr integration 0 to a. So r squared dr will give me, this will give me r cube by 3, which is a cube by 3. Okay, and here is a. So basically what will I get? Pi n b0 omega cos omega t, and there will be a cube, so a square on top, so there will be also an a square, and this whole thing will be divided by 3. Okay, so your final answer will be somewhat this. Yes, so that's the answer. So that's the expression for the EMF which is induced. Now this is the induced EMF. We can find out very easily the amplitude of induced EMF, because this cos omega t is the time varying part. So amplitude of induced EMF is the rest of it. So that will give me the amplitude of induced. So as we can write that as E can be written as E maximum. Say I am calling this one E max cos omega t. So very clearly you can say that it implies that your E max, maximum value of induced EMF, is this one. So what is this one? Pi n a square b0 omega whole divided by 3. So this is your answer, pi n a square b0 omega whole divided by 3. This is the maximum value of induced EMF. So if we want to graphically visualize it, you see this particular magnetic field B equal to B0 sine omega t. So I plotted B versus omega t graph. So B0 is the maximum value. So it is a sinusoidal graph. So the graph will definitely peak at pi by 2, then it will dip at pi, then again peak at 3 pi by 2, and it will dip at 2 pi. So this is exactly how things will work here. In this particular case, this is B0. Okay. So this is the magnetic field which we have applied externally, and the time varying EMF that you have got, or the alternating EMF which we have got, this is the amplitude of that EMF, which is E max, which we already found out. So we can call this one as the peak value. Once you know the peak value, you can find out average value, RMS value, all these things you can. That is the domain of AC. So how is the variation we want to see? We want to see that. So it is varying with cos omega t. So when omega t is pi by 2, then cos omega t is 0, right? So here it is E max. Then at pi by 2 it becomes 0. Again at pi it attains a negative maximum value because cos pi is -1. And again at 3 pi by 2 it will become 0. and then again it will go up. So this is how the EMF is varying with respect to omega t or t, whatever. You will see this sort of variation, and the applied magnetic field is this sort of variation. So this particular structure, this is a spiral plane or a plane spiral, you can say. It is a spiral, means several loops which are going one over the another, one over the another. And our goal was to find out the EMF which is induced when this particular plane spiral is placed in this time varying magnetic field. Now in certain exam this sort of question comes, that they give you that the total magnitude of induced EMF is, they tell you this one, pi s square n b0 omega cos omega t by x. Find the value of x. So here in our case the value of x will be 3. Thank you everyone. I hope this problem was useful to you and it helped to clear certain fundamental doubts of electromagnetic induction. Thank you once again. Stay healthy, stay safe. Till next time, I'll see you with another interesting problem. Till then, take care. Bye.